On wings of crimson steel. It's Elastic Collision Practice Problem 12.2 from our Work Energy Unit and Conservation of Energy. If you haven't checked out the first practice problem we did, 12.1, go check it out. It's a crazy problem with a ton of algebra steps that go in it, but the main concept of conserving momentum and conserving energy is what we're dealing with. And this problem is going to be very similar to that, but just a little bit easier. Okay? We still in this problem have two identical balls or two identical spheres, and they're colliding head-on, just like in 12.1. So this ball's going this way, and this ball's going this way. When they rebound, they're going to rebound in opposite directions. So blue's going to go left, and red is going to go right. We know that the first ball has a speed of 2.3 meters per second before the collision and 1.7 meters per second after, which really means that it's negative 1.7 meters per second because it moved in the opposite direction. We don't know anything about the first or the second ball's speed initially or after the collision. These are the two things we're looking for. And because we have two unknowns, we need to have two equations to solve them: the conservation of momentum and the conservation of energy. Now, something very fascinating about this problem is that these two balls, these spheres here that are colliding, they are identical, which means they have the same mass. And that's going to do something really, really cool when we get into our equations. Our first equation that we like to write is the conservation of momentum equation. And if we recall from Unit 7, when we learned about the conservation of momentum, that's going to be initial momentums equal to final, and momentum is defined as a mass multiplied by a velocity. So when we do this, this is like the mass of the first object, which I'm just going to write as m, because that mass is the mass of the second object. They're the exact same, so there's no reason to differentiate the masses here. But that's going to be a mass multiplied by a velocity, 2.3, plus a mass multiplied by some unknown initial velocity for our second object. These initial momentums have to equal the final. It's a mass times a final velocity, the negative 1.7, plus a mass multiplied by the second object's final velocity, which we don't know. Now, the really awesome thing about these objects having the exact same mass, and it makes this problem so much easier than 12.1, is because all the masses are the same, we can divide by mass and all the masses drop out. We don't care about them. I've said this before, and I'll say it again. If a problem doesn't give you a mass, it's probably because it doesn't matter. It either won't appear in an equation, or when it does, it will divide out. It will cancel out everywhere. So because it cancels out everywhere, this is now our conservation of momentum equation. Pretty cool. If we write out our kinetic energy equation, or our conservation of energy equation, I could say, except we don't care about gravitational potentials here because we're on a flat surface, and we don't have springs, so we don't care about those either, so we're just left with kinetics. We recall that kinetic energy is 1/2 mv squared. And because everything here is going to be a 1/2 mv squared, blah, 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 everything is going to have a 1/2, which is going to divide out. And because all the masses are the same, all the masses are going to divide out as well, leaving us only with velocity squares. So when we write this, we can write it as just 2.3 squared, because the 1/2 went away, the m went away, and we just have 2.3 squared, plus the 1/2 m go away, and now we have just the second object's initial velocity squared. This is equal to 1/2 m go away, negative 1.7 squared, plus v2f squared. So we now have our conservation of momentum equation and our conservation of energy, and in this case just kinetics, because that's all we have in this problem. So we have two unknown variables. We've got two equations. We now need to try to set up a simultaneous solver, or a substitution method as we like to use, in order to solve these out. So what I'll do is I'll go up here into this first equation for momentum, and I'm just going to solve this in terms of V2F, or I'll solve for V2F. So I'm just going to add 1.7 to the other side. And when I do this, I'm going to get the following equation. I'm going to get that V2F is going to equal, well, 2.3 plus 1.7, because that went away there, is 4 plus V2I. Now that I have this equation for V2F, I can plug it in to our kinetic energy equation. I'm going to have to be a little careful because this is a quantity that I'm going to have to square in a moment, which means that there's going to be some foiling for us to do. But let's just write this out down below. When I write this out down below, I'm going to start squaring the numbers I have. So 2.3 squared is 5.29. Then I'm going to get plus V2I squared equals, the negative 1.7 squared is going to become positive, and that's going to be 2.89. And then I'm going to have 4 plus V2I squared. And like I just mentioned, because this is squared on the quantity, we're going to have to multiply the quantity by itself, which means some foiling. Okay, so now we need to start solving this equation. And the first thing we really need to do is we've got to deal with this sucker. We've got to pull some distributions here. We've got to do a little bit of foiling and then blow this back up and solve. So let's work out 4 plus V2I times the quantity 4 plus V2I. So if I FOIL this, which is what we have to do, first outer, inner, last, I'm going to do 4 times 4 and get 16. And then 4 times V2I is going to give me 4 V2I. And I'm going to add that to the next 4 V2I, because I'm doing it on the outside and the inside. So I'm going to get plus 8 V2I. Then I'm going to have V2I times V2I, so plus V2I squared. So if I rewrite my upper equation, that blue one, I'm going to have 5.29 plus V2I squared equals 2.89 plus, and then all of this, 16 plus 8 V2I plus V2I squared. That is the equation I can play with. So at this point, we just need to combine like terms and then solve this out. And one thing that we notice that we're going to have to do here, because we've got V2I squareds, some V2Is, and then just some numbers, this is going to form a quadratic eventually, which, woof, opposite of B plus or minus the square root of B squared minus 4AC all divided by 2A. Yeah. Or Wolfram alpha that, because I don't want to do quadratics. So let's just combine like terms here and deal with this. Okay, so let's just combine some like terms here. When I subtract the V2I squared from each side, I actually get rid of it. So maybe I won't have a quadratic. I know I've solved this with a quadratic before, but maybe in this case, this drops out. We'll see what happens. We'll see if we even get this problem right, and if this video exists. But that dropped out. And then let's subtract the 5.29 from each side here. So now I've got 0 equals 8 V2I, and then some numbers. So I've got 16 plus 2.89 minus 5.29, which gives me plus 13.6. And if I just want to solve for V2I now, let's subtract the 13.6 from each side. So I've got negative 13.6 equals 8 V2I, and then we'll just divide by 8. This gives me V2I equaling, drum roll, negative 13.6 divided by 8, negative 1.7 meters per second. And that is nice. That does make some sense there. That initial velocity should be negative because it's going to the left in the beginning, which we've called in our diagram the negative quantity. So now, how do we find that final velocity for the second object? Well, we already built an equation to do this, right here. Our substitution equation is solving for the second object's final velocity. It's just 4 plus v2i. And since we know what v2i is now, negative 1.7, we can just say 4 minus 1.7 equals the second object's final velocity. 4 minus 1.7 gives us a positive 2.3 meters per second, which is making sense here because in our second scenario, this is going to the right. So those are our two answers. Now, something interesting that you might notice here is that the first object, the blue, it had an initial velocity of 2.3 meters per second going to the right. But then our final one has that velocity. And while our second object had an initial velocity of negative 1.7 going to the left, the blue object had that as its final velocity. When you have identical objects, identical masses, and they collide in a perfectly elastic collision, because the energy is conserved, effectively their velocities are just swapped. We've seen this effect whenever we have a stationary object that we hit with a moving one. The moving one stopped and the stationary one gained that speed. But in this scenario where they're both moving, they just gain each other's speeds in a full transfer because everything must be conserved. So it's a kind of wild thing there, seeing that happen, but that's what happens. It's what we see in the real world, and it's what the mathematics here just proved. So if you kind of knew that little feature to begin with, you wouldn't have to do all this math, but we didn't know that till the end, so we did it, okay? But with that, this problem is completely finished. It's a conservation of momentum, a conservation of kinetic energy due to the elastic collision. We do a substitution method. We do a bunch of algebra. We didn't need a quadratic here, the way things worked out, but maybe if you set up your substitution a little different, you may have needed a quadratic to do that, in which case, go to Wolfram Alpha, type it in, and get something to kick out. But in our case, we could just solve and then plug back in. So this problem is finished. We're going to do one more practice example, 12.3, where we have a stationary object, but we're missing a little bit more information. So once again, some substitution is going to come up. Check out that practice problem. And until next time, adios, and take it easy.